Thank you. Okay. Hello, everyone. I'm Vasudev Gohil. I'm currently with Siemens, and this is work that I did during my grad school at Texas A&M University. So in this talk, I'll be presenting this work called LLMPirate, where the idea is we explore essentially how large language models can assist in pirating hardware circuits. The abstraction level that I'll be talking about is very different to firmware. We are talking about gate level netlist, so that's where most of the discussions will be. All right, so it's no surprise to anyone here, language models are everywhere. People have explored them in finance, education, science, even in software fuzzing to find bugs, and even in semiconductor chip design. So these language models have shown a lot of promise in all these areas, but along with that, there have also been several attacks that can be launched using these language models. A few examples are shown here. For example, researchers have shown that they can be used to generate malware. They can be language models can be poisoned to generate malicious codes and stuff like that. So along those attack lines, what we want to explore over here is, can we use these language models to pirate hardware circuits or intellectual property in terms of hardware circuits, right? And the answer, of course, is affirmative, and we show that using this technique called LLMPirate. So before I go into all the details of what we do and how we achieve this piracy, I just want to set the threat model clear. So we assume there's a piracy detector that essentially compares two different or potentially the same circuits and determines whether one is pirated from the other or not. The first constraint that we set on this technique is that we cannot make any modifications to the detector, so it's as is. We cannot change its internal parameters. If it's a machine learning technique, we can't change the weights and biases. We can't poison the model, inject bad examples into training and things of that sort. The second assumption is that we simply prompt the language model using this gate level netlist and expect it to generate a pirated netlist. The idea of a pirated netlist is that it needs to maintain the functionality as the original netlist, but change the structure, which is the interconnections and the gates, so that the piracy detection tool cannot classify it as the same circuit. And the third assumption, or the third constraint we make, is that we don't have white box access. We essentially have a black box access to the piracy detector, so we can't even view the internal parameters or any internal details about the detector. We just get a final output saying that whether this is pirated or not. And that's the whole idea. We want to, under these three constraints, we want to see how can we use language models to evade these piracy detection tools. All right, so with this threat model in mind, let's talk about what we do. Okay, so we start with a very basic formulation. We simply take a language model off the shelf, something like ChatGPT, and then we prompt it with a Verilog netlist saying that, hey, this is a Verilog netlist. Can you refactor or rewrite or rephrase this netlist in a way that it's structurally different but functionally identical to the original netlist? And what we see, unsurprisingly, is that it doesn't work at all. The language model fails terribly in understanding what Verilog is, and it doesn't. A lot of the times, it doesn't even generate a syntactically correct netlist, and that's not surprising, right? Because these language models are trained on a large amount of C, C++, or software codes, but very limited amount of Verilog data, let alone netlists, right? So that's the first challenge that we observed when we had this, when we went about this project, is that these language models don't really understand Verilog very well, and especially netlists, which are gate-level netlists. So that's the first challenge. So to kind of overcome this issue, what we did was we translated these netlists. We essentially wrote a parser that translated these netlists into a Boolean operator format. So for example, if there's an AND gate that's kind of ANDing two signals and producing an output, we represent that as a Boolean AND operator ANDing two variables, right? So essentially, we do a syntax translation from a gate-level netlist to a Boolean operator space, and that helps the language model understand what's going on. The second issue that we came across when we tried to scale this is Verilog netlists are huge. They contain hundreds of thousands of gates sometimes. And the context windows of language models are typically of the order of tens to hundreds of thousands of tokens. So we cannot fit entire Verilog netlist into the language model to prompt it and generate a pirated netlist. So the obvious solution over here is we divide and conquer. But what we essentially do is when given a Verilog netlist, we first characterize it and understand what are the different types of gates and elements that are used in this netlist. And then for each of those different types of elements or gates, we prompt the language model to rewrite or restructure it. So essentially, it's a very granular kind of division of the netlist into parts, and then we one after the other feed the language model to rewrite each different part of the netlist. All right. And then after that, the third problem over here is that sometimes, because these language models are non-deterministic, they make mistakes. But the good thing about language models is also that they are kind of inclined to correct their mistakes if they are provided some feedback. So we essentially put this entire thing into a loop. And if, for example, the language model generates a response or a circuit that is not functionally identical to the original circuit, we say that, hey, this is wrong, can you please try again? Something as simple as that. And essentially, so what we do is just have this entire thing in a loop and provide feedback to the language model depending on whether it's functionally equivalent or not, whether there's any syntax issues or not, and things like that. So that's the whole idea of what we do and how we achieve this piracy of hardware circuits using language models. I'll just go through the steps one by one so that it's a little more clear about what happens when. So let's say we are given a bunch of netlists or even a single hardware netlist that we want to pirate. The first thing we do is what I talked about in solution B, which is we characterize this netlist and extract all the different types of gates that we have in this netlist. Then we iterate over each of those gates. So for each of those gates, we convert that gate level representation into a Boolean operator representation, which is the prompt syntax translation that I talked about. And then we feed that prompt to the language model. We test a whole bunch of different language models. We just pick one of them in this example over here and then get the response for that language model. Once we have this response, we analyze it for syntax checks, for checks whether it's using the correct operators or not, and whether it's the functionality of this rewritten netlist or rewritten Boolean logic is identical to the original logic or not. And again, if any of those checks fail, we provide the corresponding feedback to the language model. It's very simple. And then once all the checks are passed, we essentially have a mapping or a transformation of sorts that maps a given gate or an element in a netlist to a functionally equivalent but structurally different element or set of elements in the transformation space, right? So once we have all these different transformations, we can essentially just write a very simple replacement kind of a script that kind of goes through the netlists, the elements of the original netlist, and replaces them with these transformations to obtain the pirated netlist. And that's what we query the piracy detection tool with. So that's the whole flow of how we go about pirating netlists. All right. So next I can talk about the main results. I'll talk about just the key results over here, and then you're obviously free to take a look at the main paper to see the more details. All right. So we test this LLMPirate technique on a bunch of different academic benchmarks and open source processors. So those are shown on the x-axis on the figure. And then on the y-axis, we have different detection tools or piracy detection tools or similarity detection tools. They range from machine learning-based techniques such as GNN for IP that's shown in the top row over there, top subplot. And then we also have some traditional hashing-based similarity detection tools such as MOS and SIM that are not machine learning-based but more deterministic. So we test essentially different detection tools for different benchmark circuits. And what we observe is that for all of them, in the best case, we are actually able to have similarity scores that are lower than the corresponding thresholds. So let's take the example of GNN for IP, which is the first subplot over here. The similarity scores for that technique range from -1 to 1, with the classification threshold being 0. And what we observe is that for all of the circuits that we test, we are actually able to fool this detection technique into saying that these two circuits, which are actually the same circuit or pirated circuits, are not pirated. And we observe similar results for almost all of the detection tools for all circuits. All right. The second result that I want to talk about is this ablation study. So we wanted to understand how important these different solutions or optimizations that we made are to the overall framework, right? So again, over here, the columns correspond to the different detection tools, GNN for IP, MOS, JPEG, and SIM. And then the rows correspond to different ablations that we do. So for example, the first row says LLMPirate except for solution A. So it's everything in LLMPirate, the final formulation, without the prompt syntax translation. And similarly for the other solutions as well, right? So what we observe is that if we don't include solutions A or B, which is prompt syntax translation or the breaking of larger circuits into smaller components, there's no hope. Essentially, these language models are either not able to understand what Verilog syntax is or not able to generate functionally equivalent circuits, and we are not able to evade any of the detection tools. Whereas for solution C, the story is a little bit different. If we only have solutions A and B, which is we only have prompt syntax translation and divide and conquer, we are still able to achieve a reasonable evasion rate against a bunch of different detection tools, except for this tool called SIM. But solution C does actually help improve, kind of extract that last bit of juice out of the technique by improving or boosting the evasion performance. So essentially what we observe, the final one-line summary of this slide would be that solutions A and B are absolutely essential to make this technique work, but this feedback helps a little bit. Okay. So yeah, like I said, I have a lot of other results in the paper as well, but I just want to summarize the key findings from all of those results over here. So the first thing that we observe is that model size does matter a lot. So we tested on 8 different language models of different sizes, open source and closed source. And what we observed is that closed source language models, which are presumed to be much larger than the open source language models, do very well. And that can also be corroborated by this observation that when we test the same language model with different sizes, which is code llama 13 billion versus 7 billion, 13 billion does much better compared to 7 billion. The other observation that we had is that training data size is also very important. And that can be seen by this observation where if we evaluate this technique on an older generation Llama 2 language model, it does worse compared to this newer generation Llama 3 language model, which are essentially the same size, but just the training data size for Llama 3 is much larger compared to Llama 2. And then the final observation that we have is that this feedback improves performance, especially for the smaller language models. So initially, without any feedback, these smaller language models like Llama 2 or Llama 3, they perform very bad. But then with this feedback, they're actually able to correct their mistakes and result in a functionally equivalent but successful piracy against these detection tools. Yeah, that's all of my presentation, and I have some references if you're interested. Thank you.
Okay. So if you have questions, please come to microphone. For your tool, for the detection tool you used, they probably don't know you have the LLMPirate, this tool, right? Let's assume I'm a detection tool designer. I know your system.
Mm-hmm.
Can I write a detection tool to detect your approach?
That's a great question. Yeah, actually, that's one of the countermeasures that is possible. What can be done is, especially for these machine learning-based detection tools, right? They can be trained on these, essentially the way that I think of these pirated circuits is adversarial examples. If you train your machine learning tool on this new set of pirated examples, then you can potentially improve your performance. Yeah.
Hi, Mitchell Dickerson from University of California, Irvine. Fascinating work. When you say it preserves performance, does that include critical path and timing closure?
That's a great question. So it preserves functionality. That's guaranteed. We did formal verifications to ensure that the functionality is the same. But in terms of timing violations, not violations, but like the critical path delays, right? So we do observe some overheads in terms of critical path delays. I think the overheads are of the range of 10%, if I'm not wrong. That's something that's present. But I think one way that can be mitigated, which we didn't explore in our work, is once we have these replacements, like the transformations that we obtain from the language model, we just simply put it in just copy and paste. But there's also a possibility of kind of optimizing once we have this pirated netlist to optimize it using one more run of synthesis. That's something that we've not tried.
Thank you.
Thank you.
Do we have more questions? Okay, let's thank the speaker one more time.
Thank you.